In this video tutorial, we're going to take a look at something called Pascal's triangle. And mathematicians have known about Pascal's triangle for hundreds and hundreds of years. The current form it's in is named after a mathematician called Blaise Pascal. And the way Pascal's triangle goes is it starts with a leading 1 on top. And then we go 1, 1. And every row actually has a 1 at the beginning and then 1 at the end. And one of the patterns that we'll talk about is how you get the next numbers in the next row. So it starts with a 1, and this 2 comes from adding these two 1s. So 1 and 1 add to 2. Okay, so next row starts with a 1, 1 and 2 add to 3, 2 and 1 add to 3, ends in a 1. Okay, so it starts with a 1 here, 1 and 3 add to 4, 3 and 3 add to 6, 3 and 1 add to 4, ends in a 1, etc. So if the next row is 1, 5, 10, 10, 5, 1, to get the next numbers, I would start with a 1, and then go 1 and 5 add to 6, 5 and 10 add to 15, 10 and 10 add to 20, 10 and 5 add to 15, 5 and 1, 6, ends in a 1. Next row starts with a 1, 1 and 6 add to 7, 6 and 15 is 21, etc. So that's the next row. Now, these numbers down here, actually, every row can actually be expressed using combinations. In order to use combinations, though, we start counting with the n value. Remember, NCR is the terminology for a combination. We actually start counting at 0 instead of 1. So the first row actually uses an n value of 0. The second row uses an n value of 1. The third row uses an n value of 2. Notice that the second number at each row is actually the n value. So 2 here, this would be the n equals 3 row, the n equals 4 row, etc. n equals 5, 6, 7. So the numbers are going to be always n choose 0, and the r starts counting at 0. The second number in the combination, it starts counting at 0 also. So n choose 0, n choose 1, n choose 2, n choose 3, etc. Up to the last one would be n choose n. Anything choose itself is always 1. That's another reason why every row ends in a 1. Anything choose 0 is also 1. That's why every row starts with a 1. So of course these coefficients, n choose r is n factorial divided by r factorial and n minus r factorial. So the combination formula we can use to find any number in Pascal's triangle as long as you know where it is. So the symmetry pattern, if you draw a vertical line down through the middle of the Pascal's triangle, notice that these numbers on this side are duplicated over here, just in reverse order. 1, 4, and after the 6 goes 4, 1. 1, 5, 10, and after the middle goes 10, 5, 1. Now I want to draw your attention to the fact that any combination has an equivalent combination. It's right up here, n choose r is equal to the combination n choose n minus r. Notice that whatever numbers these are, this one and this one, if I add the r value and this n minus r, notice that the r's are opposite, so we got r and negative r, so they add to 0, so that actually simplifies to n. So what I'm saying is that this number and this number here, the second numbers, always add to whatever the n number is. So note, for example, okay, this number here, here, that's actually 5 choose 2. This number here is 5 choose 3. Notice that they're the same. And we're just going to prove that using the combination formula. 5 choose 2 would be 5 factorial over 2 factorial, and then also 5 minus 2 is 3 factorial. If we use the combination formula to do 5 choose 3, get 5 factorial on top, and then there's also 3 factorial down here, and 5 minus 3 is 2. Notice it doesn't matter whether you say 3 factorial times 2 factorial or 2 factorial times 3 factorial. That denominator is the same, and of course the numerators are both 5 factorial, so they would have to be the same. The recursive pattern, the adding to get the next number. So that's a 1, 1 and 5 add to 6, 5 and 10 add to 15, 10 and 10 add to 20, 10 and 5 add to 15, 5 and 1 add to 6, and we have a 1 in the end. Okay, so now notice I have these different color. The 5 and 10 add to 15. So this is how you write this one as a combination formula or equation. Um, if you take any number like the 5 here and call that n choose r, we're adding to it the next number in the same row. So that's why, notice that these two n's are the same, and this number is one bigger than this. So it's the next number in the same row. It equals a number in the next row. So if this is n, then the combination over here is n plus 1. It's one bigger. And it's in the same position. So you see the 10 is the third number in this row. The 15 is the third number in the row below. So that's why the second number in this combination is the same as that. N choose r plus 1, n plus 1 choose r plus 1. So my example here was that 5 and 10 add to 15. See, 5 is actually 5 choose 1. 10 is 5 choose 2. Remember, you start counting at 0. This is the 0th number. Okay, this is r equals 1, r equals 2. So that's why 5 choose 2. This is the n equals 5 number here. It equals the 15. The 15 is actually from the n equals 6 row. And remember, you count 0, 1, 2. So it would be 6 choose 2. So 15 is 6 choose 2. This is called Pascal's identity. Here's another example. Let's say further down Pascal's triangle, we had 20 choose 3 and 20 choose 4. They're in the same n equals 20 row. The r equals 3 number and the r equals 4 number. So it equals the combination in the next row. So the combination has to start with 21. And it's 21 choose 4 because it's in the same position in the next row as this number was. Just like the 10 is the third number in this case, and the 15 is also the third number. Remember, it's choose 2 because you go 0, 1, 2. Remember, you start counting at 0. So that's Pascal's identity. Another pattern, a diagonal pattern, and I'm going to highlight 3 of them here. These values, these shapes are in the shape of a hockey stick. Again, the very Canadian thing. This is called the hockey stick pattern. And notice that 1 and 6 add to 7. 1, 5, and 15 add to 21. And the green one here, 1, 3, 6, 10, and 15 add to 35. Okay, so this is another pattern from Pascal's triangle. There's lots of patterns in Pascal's triangle. The green one here, the 1, 3, 6, 10, and 15, the 1 is actually, see, it's the n equals 2 row, so that would actually be 2 choose 2. This number here is in the n equals 3 row. Remember, you count 0, 1, 2, so that would be 3 choose 2. This would be 4 choose 2, 5 choose 2, and 6 choose 2, because it's the n equals 6 row. Equals the number in the next row, so that's why it's 7 choose, and it's the next one after. See, you go over this way, so you see that's the 4th number in this row. This is the 3rd number, so it's the next one past this one. Remember, you start counting at 0, so 0, 1, 2, so that was 6 choose 2. This would be 7 choose 3 because we're in the n equals 7 row, and you start counting at 0, 1, 2, 3. So in the combination I'd use 3, 7 choose 3. So that's the hockey stick pattern. So in this page, we're going to take a look at writing combinations as an equivalent combination or a couple of combinations add to. And so this first one here is the two identical combinations. N choose r and n choose r minus 1 are always going to be the same. So an equivalent combination for 10 choose 3 would be 10 choose 7. Again, 3 and 7 add to the 10. Okay, so that's how I know it's going to be 10 choose 7. 10 choose 3 and 10 choose 7 are the same. I can verify that with my calculator. If I bring my calculator over here, 10 choose 3 and 10 choose 7 are both 120. So there's an example to show that. Next one, 8 choose 5 and 8 choose 6. This is the Pascal's identity. We're adding 2 numbers to get the next number in the next row. Notice that these are both in the n equals 8 row and they're consecutive numbers. This is the r equals 5 and r equals 6 number. So in the next row, it would be, and this n choose r plus n choose r plus 1 is equal to n plus 1 choose r plus 1. That's how you state it with combinations, with the formula. So it's the next row, so n would be 9. And it's in the same position as this one. So that's why the combination would be 6. Remember, see, this is r plus 1. This is also r plus 1. In C, an equivalent combination here, same formula as up here. 50 choose 45 would equal 50 choose 5. Again, this number and this r number add to the n number. 45 and 5 add to 50. And you could demonstrate that with the calculator too. D, 23 choose 8 and 23 choose 9. So in the n, they're both in the n equals 23 row, consecutive, 8 and 9. So this would equal the number in the next row. Okay, same as here. So it would be 24. So n equals 24, and same position as this one. So 24 choose 9. Example 2. What's the fourth number in the 60th row of Pascal's triangle? So you don't want to write out all those rows. So in the 60th row from the top, n would be 59. The fourth number, you go 0, 1, 2, 3. Okay, so r would be 3. Remember, you start counting at 0 for both n and r. So that's why 59 choose 3 would be the fourth number in the 60th row. So 59 factorial divided by 3 factorial, and 59 minus 3 is 56 factorial, which is 32,509. So that is the fourth number in the 60th row of Pascal's triangle. Now, some patterns, the last few pages here, have to do with something called the Binomial Theorem. And we're just really going to touch on this. Patterns in binomials. If you're expanding binomials, the binomial a plus b, remember it's called a binomial because there's two terms, anything to the power of 0 is 1. If you evaluate a plus b to the first, you get a plus b. Okay, so that's the simplest of the two. Now, if I want to go a plus b squared, and I'm actually, now the long way to do this, a plus b squared, means you have an a plus b times another a plus b. So you're multiplying two of them. That's a b. Hence, the exponent is 2. So if you multiply these together, remember you multiply everything in one by everything in the next. So we would go a times a is a squared. A times b is an ab. Now I've done the a by both terms in the second one, so I'll do the b now. So b times a would be an ab. Plus, last term comes from multiplying this b and this b, which would be b squared. So we have a squared, 1ab, and 1ab would be a 2ab, and plus b squared in the end. So that's where that comes from. This is going to be a shortcut so you don't have to multiply all these binomials together. Of course, to get the next one, let's go back to the arrow here. I could take this and multiply by another a plus b, because this is cubed now, and I would get these three terms. Now notice that the coefficients 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1 are actually the numbers in Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 5, 10, 10, 5, 1. It's actually a 1 here and a 1 here. Another pattern here is when you're doing the expansion. So for example, the a plus b to the fourth, okay, it is the n equals 4 numbers from Pascal's triangle row. You go 1 here, and then the first term in the binomial is raised to the power of this exponent here, so it's power 4. And then after the 4 we go this, and then what happens to the power on the a is it decreases. It goes 4 here, and then 3, and then 2, and then 1. There's actually a to the power 0 here, although we don't normally write it. The b here starts actually with the power of 0 here, but we don't write it because b to 0 is 1. And then it goes b to the first, b to the second, b to the third, b to the fourth. Okay, so notice that this exponent starts here and goes down by 1 each time. This exponent starts at 0 and counts up to the power 4. Similar idea with the a plus b to the fifth. It's fifth, so we use the n equals 5 row, 1, 5, 10, 10, 5, 1. So coefficients are 1, 5, 10, 10, 5, 1. And the power on the a starts at 5 and then counts down by 1 each time to 0. The power of the b starts at 0 and counts 1, 2, 3, 4, up to 5. So that's some patterns, and that's actually the binomial theorem and how you can use it to expand it a binomial, because to actually multiply 5a plus b's together is a lot of work. Okay, this was only 2. To do that 3 more times is a lot of work. So what we're going to do in this example is write the expansion of each binomial. So this is x plus y is evaluated to the power of 7. So the n equals 7 row of Pascal's triangle is 1, 7, 21, 35, 35, 21, 7, 1. And of course, we can go back. See, here's the 7 row. 1, 7, 21, 35, 35, 21, 7, 1. You can get all those, of course, using combinations too if you want. So we start with x to the power of 7. There's actually the 1 here means the coefficient is 1. If you want to write 1x to the 7th, you can, although coefficient is 1, you don't normally write it. So 7 is the next coefficient, so we put 7 here, and then the exponent on this goes down by 1 to 6, and the y starts to the power of 1. There's actually a y to the 0 here, but we don't normally write that. So the next coefficient is 21, so we put a 21 here, and then the exponent of the x goes down by 1, the exponent of the y goes up by 1. Next term is a coefficient of 35. X goes down by 1, y goes up by 1. 35 again. X goes down by 1 to 3, y goes up by 1 to 4. Notice that the exponents in any term would always add to this exponent here, this power. So 3 and 4 add to 7. 5 and 2 add to 7. 6, and there's a 1 here, add to 7. Next coefficient, we've used the two 35s. Next one's 21. So 21 here, x it becomes squared, the y becomes power of 5. And then using the 7, okay, x to the first, y to the 6, and then the last term would be 1, y to the power of 7. There's actually an x to the 0 here, but we don't write it normally because x to the 0 is 1. So y to the 7 is the last term. Now, the only difference in b here is I have a minus sign. And the only difference that makes is that every second sign is the opposite. All the same terms here, except this would be a negative, and this one, and this one, and this one. Okay, all of the even numbered ones, because the second, the fourth, the sixth, the eighth, etc. So, and actually the reason for that, because remember an odd power of a negative is negative. So the exponent of the y is 1 here. That's why this term ends up being minus x to the 6y. See, this term is positive, but the next one's negative because the exponent on the second term is odd. That's why it's a negative here. And then, okay, so this is going to be the same, but then we have a minus 21 x squared y to the fifth. And this would be the same, but then this is going to be a minus on the end. Okay, so that's the only difference changing that sign makes. Now, in C here, there's a little bit more to this because it's not just an x and just a y, or just an a and just a b. So the n equals 5 row of Pascal's triangle is 1, 5, 10, 10, 5, 1. You can look on the previous page to see that too, or use combinations. So the first we would start with is 1 times the whole 2x, that's the first term in the binomial, raised to the power of 5. And then the next coefficient is 5. So we put a 5 here, and the 2x exponent reduces to 4, and the y cubed becomes a 1. There's actually a y cubed to the power of 0 here, but we don't normally write that because it's 1. So we've used the 5, now we do 10. So 10, and the exponent of the 2x becomes a 3, and the exponent of the y cubed becomes a 2. It increases to 2. Okay, remember, first one goes down, second one goes up. We've used this 10, but we now need this one. So 2x cubed becomes 2x squared. The y cubed squared becomes y cubed to the power of 3. Use the second 10. Now we have a 5. Exponent becomes a 1. This one becomes 4. And then on the very end, it's 1 times, and the y cubed goes to the power of 5. You could write a 2x to the power of 0 in there if you wanted, but again, that would be 1. That would be 1. So now what we need to do is simplify each individual term. So 2x to the fifth. Now, a lot of people, a very common mistake here is a lot of people forget to raise the 2 to the power of 5. So 2 to the power of 5, and I didn't mean to bring that one up, is 32. Again, we could bring the calculator over. 2 to the power of 5 gives us 32. So that's why that's 32. And then, of course, you also raise the x to the power of 5. Okay, next one. Now what I'll normally do here is do each individual part by itself. So we have 5 here. 2 to the 4th is 16, x to the 4th is x to the 4th, and we have y cubed to the 1st is y cubed. And I'll multiply those in the very last step here. We have a 10 here. 2 cubed is 8. 2 times 2 times 2 is 8. X cubed is x cubed. Y cubed squared. Well, remember, power for power, you multiply the exponent. So 3 times 2 gives you y to the 6. Again, now we have 10. 2 squared is 4, and x squared is x squared. Y cubed times the 3's gives you 9. 5 and then 2x, and y cubed to the 4th, multiply the 3 and the 4 to get 12. And then we have y to the 15th in the end. 3 times 5 is 15. Now we'll simplify each individual term. So the 32x to the 5th is already simplified. 5 times 16 is 80, and it'll be x to the 4th, y cubed. 10 times 8 is also 80, x to the cube, y to the 6th. 10 times 4 would be 40, x squared, y to the 9th. 5 times 2 is 10, so 10 and then x, y to the 12th, and we have the y to the 15th on the end. And so that's the whole expansion. Now it does seem like a lot there, but if you actually had to multiply 5 of these 2x plus y cubes out, it's going to be more than this, a lot more. So this really is a shortcut. Last example on the last page here. So we've got 3x squared, so this is very similar to the previous one, minus 4y cubed to the power of 6. Now the exponent is 6 here, so we need the n equals 6 row. And it's 1, 6, 15, 20, 15, 6, 1. So we start with a coefficient of 1, and you can write that here if you want, but you don't have to. So we do 3x squared to the power of 6, starts at 6. Now remember, there's actually a negative 4y cubed to the power of 0 here, but we don't normally write that. Next coefficient is 6. We put a 6 here. And we go 3x squared, and then this reduces by 1, and this one becomes the power of 1. And then we have the 15 next. This becomes the power of 4, negative 4y cubed to the power of 2. Okay, it goes up by 1. Now let's do the 20. This exponent on the 3x squared reduces to 3. This one increases to 3. We've used the 20. Now we need to do the 15. This exponent becomes 2. Okay, remember it reduces by 1. This one will increase by 1. Remember, the 2 and the 4 add to the 6. So I've used the 15. Now I need to do the 6. So I'll start in the next line here. 6, and then this exponent reduces to 1. This one increases by 1 to 5. And the last term would be 1, and it'd be just negative 4y cubed to the power of 6 now. There is 3x squared to the power of 0 here, but we don't normally write that. So let's simplify the individual parts. So 3 to the power of 6, 3 to the power of 6, there's where the 729 comes from. And then next we go 6 and 3 to the 5th is 243. Power for power, you multiply exponents. So 2 and 5 multiply to 10. And times this. This is the first power, so it's just negative 4y cubed. So 15, and then 3 to the 4th is 81. X squared to the 4th, remember we multiply the exponents, so 2 and 4 multiply to 8. And negative 4 squared is 16. Y cubed to the 2nd, remember you multiply the exponents is 6. Notice that you see the power of 2, okay, this can be positive here, but the power of 1, 1's an odd number, is negative, so that's why this term is going to be negative, because we have an odd exponent on that negative. So next here, 20 and 3 cubed is 27. X squared to the 3rd, multiply exponents, 2 times 3 is 6. And negative 4 cubed is negative 64. So remember, positive term here, we've got a negative here. Y cubed to the 9th, 3 to the 3rd is 9. 15, and then 3 squared is 9. Squared, 2 times 2 is 4. Negative 4 to the 4th is 256. And y cubed to the 4th, multiply exponents, 3 times 4 is 12. This one next, we have 6 here, 3x squared, so nothing to evaluate there. Negative 4 to the 5th is negative 1024. And y cubed to the 5th, 3 times 3 is, 3 times 5, sorry, is 15. And on the end here, negative 4 to the 6 is, maybe I'll do one last one here, negative 4 raised to the power of 6 is the 4096. I actually could have just done this because it's a negative base but an even exponent, so it is going to be giving 4096. And 3 times 6 is 18 from the y. So the 729 x to the 12th is good. 6 times 243 times negative 4 is negative 5,832, x to the 10th, y to the 3rd. 15 times 18 times 16 is 19,440, x to the 8th, y to the 6th. Next we go 20 times 27 times negative 64, I think I clicked twice, is negative 34,560, x to the 6th, y to the 9th. Next we go 15 times 9 times 256, which is this same number actually, 34,560. This is positive because we have all terms are positive here. This one was negative because of that odd exponent there. So an x to the 4th, y to the 12th. 6 times 3 times negative 1024 is negative 18,432. X to the 2, y to the 15th, and then the 4,096, y to the 18th in the end. And that's the end of the video.